All right, so let's get back to talking about the structure of the periodic table and particularly the groups and families of the periodic tables. You'll remember that groups are columns and they have similar chemical properties because they have similar electron configurations. So our first group here, the first column on the periodic table are the alkali metals. Notice I start with lithium and not with hydrogen. Hydrogen is not a metal, although it has the same electron configuration in its element form as the other elements. Because it's in that first period, it lacks other properties that metals would have. So hydrogen is not a metal. Right next to that, we have the alkaline earth metals. So be careful with that pronunciation and writing. Alkali metals is the first group. Alkaline earth metals is the second group. And these are elements with 2 electrons in an s sublevel. Jump into the other side. Right next to that last column, we have elements with nearly a full p sublevel. So these elements referred to as the halogens will very easily gain electrons, particularly 1 electron, to get to that noble gas electron configuration. And of course, next to our halogens there, we have our noble gases. These are elements with a full S and P sublevel at the highest energy level, of course with the exception of helium, which only has that one S2 electron configuration because there's no P sublevel in the first energy level. Next, we're going to take a look at this dividing line. So this stair-step line that runs along boron, silicon, arsenic separates the metals from the non-metals. So everything to the left of that stair-step line is considered a metal. Everything to the right of that stair-step line considered a non-metal. We're going to keep things pretty simple in here, and we're just going to make the metal-non-metal distinction. However, there is an overlapping category of things adjacent to that stair-step line referred to as metalloids. These are things that have some metallic and some non-metallic properties. Of course, a really important one there would be silicon. There at number 14, which its metalloid properties make it really, really good for computer chips. But primarily, we're just going to worry about the stair-step line, its location, and distinguishing metals from non-metals. We jump into the middle. We have this big block of elements in the D block. The D block elements are referred to as transition metals. So they're separating our alkaline earth metals from the non-metal side. And then we have this big chunk or this strip of elements, which of course we know insert into the bottom of that table to produce the expanded periodic table. Independently, they're known as the lanthanide and actinide series because they actually start not with 58 and 50, but they start with, 90. They start with 57 and 89, which are lanthanide and actinide. But these elements collectively, both rows, are referred to as the intertransition metals. Intertransition metals, again, between the alkali metals and the transition metals. So intertransition. We have just a chunk of things under the stair-step line, right? The bit there that are not considered metalloids are just other metals. So we have in there some important ones. Tin and lead are fairly common. Aluminum are fairly common metals used in all kinds of features of life. All right, so back to our condensed form of the periodic table. We want to pay special attention to the S and P blocks combined. The S and P blocks combined are S and P blocks combined are referred to as representative elements. Representative elements are so called because they're things gaining and losing electrons to get to those noble gas electron configurations. So they're things that are filling S and P sublevels, and typically their chemistry is about gaining or losing electrons to get to noble gases. Whereas transition metals, intertransition metals, for the most part, are too far away from the noble gases for that to motivate their chemical properties. So again, we have our condensed form of the periodic table. We need to be able to think about all of these groups and be able to identify them elements by their groups and by their chemistry, because of course that chemistry is related to their electron configurations. And so the organization of the periodic table is primarily an off-bow organization. And that off-bow organization allows us to predict electron configurations, allows us to predict chemistry. That said, this is mainly a historical contingency that we settled on this arrangement of the periodic table. And as we've said in previous videos, this is fairly iconic. Like, it's not hard for people to pick this out when it's presented to them, but there are any number of ways that this could have gone. And I just want to wrap up this video by just walking you through a series of other options for arrangements of the periodic table. Here we have a kind of spiral form where we're starting with the lowest energy elements first, all the way up through the highest energy levels being filled, so hydrogen, helium, lithium. The groups are still sorted out by color, but again, the spiral then allows you to have all of the elements on the same page. Here is another version of the spiral, but this one works inside out. Hydrogen and helium are on the inside, and so this is essentially taking the current periodic table and putting it into a spiral form. You still have kind of those gaps where there are no P's and no D's in the lower energy levels. Here's another version of this. You can see your lanthanide and actinide series here. So we have different size groups for the S, P, D, and F sublevels. Here's one that looks an awful lot like it's some kind of child's board game. I'm not sure that the condensing of this compensates for the complexity of it, but again, in large part, it has a lot to do with what you are and aren't used to in terms of seeing representations of this. Here we have another kind of spiraled form of the periodic table, and so there are different things to look at in terms of how this is particularly organized. This one I actually find particularly interesting because of a different choice that was taken in terms of electron energy levels. So rather than organizing the energy levels into rows and having the sublevels be the blocks, S, P, D, and F, this is putting the energy levels in blocks. So here you have your first energy level, which only has 2 elements in it. Your second energy level, S and P, so 6 electrons in the S and 2 electrons in the P, gets you up to 8, and there are 8 elements in this block. Then we have the third energy level, SPD, fourth energy level, SPD and F, fifth energy level, SPD and F, and then the sixth energy level doesn't fill all the way up to the D and the F, or at least at the time this periodic table was named. And then, of course, at our lowest energy level, we only fill the 7s. Here is another arrangement of the periodic table, but this one is very similar to what we've seen, but everything is shifted over and the S block is moved over to the right side so that you can just keep things in number sequence. So here is 1S, here's 2S, then 2P, then 3S, 3P, 4S, and then it goes 3, 4, 5, 3, 4, 5, right? So this allows you to count in sequence by moving that S block to the right side and moving it up 1. Whether or not that pays anything off for us, I'm not entirely sure, but this is just another arrangement. So any number of arrangements of the periodic table could have been the arrangements that we landed on, but we have one in particular that is kind of the result of history, and we're going to continue to dive into its structure in the next couple of videos.